Everybody. I am Bharathi from Sri Saratha College for Women, Autonomous, Salem 16. I am going to explain about Orgel diagram. Orgel diagrams are the correlation diagrams. It is given in graphical representation. The spectroscopic state can be reduced to the graphical representation for the two correlation diagrams. These diagrams are developed by L.E. Orgel, so we called it as Orgel diagram. Orgel diagrams cover only high spin complexes. It only account for spin allowed transition. These are used for qualitative purpose only. These are the main theme of Orgel diagrams. So it is drawn between energy versus ligand field strength. The Orgel diagrams are correlation diagrams, which shows the relative energies of electronic terms in transition metal complexes. It is restricted to weak field ligands. That is, it is only applicable for high spin complexes and shows only allowed transition. Because Orgel diagrams are qualitative, no energy calculations can be performed for these diagrams. It shows only the symmetry states of the highest spin multiplicity instead of all possible terms, unlike TS diagram. For weak field method, the electron-electron interaction, that means interelectronic repulsion, is more significant. Let us see in detail. A term symbol is a shorthand notation that describes the electron distribution in atoms or ions. It involves spin-spin, orbital-orbital, and spin-orbital interaction. A term is a general grouping of energy levels, while a state is more precise and detailed description within that term. The total orbital angular momentum and spin angular momentum together specify a term. The L, S, and J specify a level, and L, S, J, and MJ specify a state. The spectroscopic terms are capital S, P, D, F. And the L value for the spectroscopic term, S is equal to 0, P is equal to 1, D is equal to 2, F is equal to 3. The S term transformed into A, P term transformed into T, D term is split into capital T and E. F term is split into A, T1 and T2. The A is singly degenerate or non-degenerate. Degenerate is the term which used for the same energy level. Here only one orbital is present, so it is singly degenerate or non-degenerate for S term. P is triply degenerate, D is triply degenerate and doubly degenerate, and F is single degenerate and two triply degenerate. Now, we will see about the SPDF spectroscopic terms in detail. An s orbital is spherically symmetrical, so it is non-directional in nature, and hence it is not affected by any other field. Here, no splitting is involved. Its spectroscopic term is capital S. The p orbitals are directional, but they have same type of orientation. They are affected by the octahedral field, but to an equal extent. Their energy levels remains equal and no splitting occurs. Its spectroscopic term is capital T. Then a set of 5d orbitals split by an octahedral field into two levels, that is capital T and capital E. Its spectroscopic term is D. The capital D split into triply degenerate and doubly degenerate E components. The last one is a set of 7 f orbitals is split by an octahedral field into three levels. Its spectroscopic term is F. It's split into two triply degenerate T1 and T2 and singly degenerate A components. In an octahedral field, the S and P are not splitted. D states are splitted into two states, and F state are splitted into three states, and G states are splitted into four states. These states splitted by the external field are called Mulliken symbols. The symbols are used extensively in interpreting electronic spectra of transition metal complexes. The splitting of terms of free ions or atoms into Mulliken symbols in an octahedral or tetrahedral field. In the case of octahedral, the G term is used. G means gerade. Gerade means the octahedral complex possess center of symmetry. So we have to put G. But in the case of tetrahedral field, we have to ignore G because there is no center of symmetry is present in the complex. Now, the two Orgel diagrams, there is two Orgel correlation diagrams or D Orgel diagrams, which include D1, D4, D6, and D9 configuration, and F Orgel diagram includes D2, D3, D7, and D8 configuration. The D1, D4, D9, D6 complexes gives only one absorption band. The D2, D3, D7, D8 complexes gives three absorption bands. D5 complex consists of a series of very weak, sharp absorption bands, which are highly intense. In the case of the D5 configuration, have more absorption bands but have short one. Now, let us see the correlation diagram for D term. The correlation diagram is plotted between energy versus Ligand field strength. The center part is zero Ligand field strength. It increases from left to right and right to left, the Ligand field strength. is increases gradually from 0 to right side as well as left side. Here it increases. There also the field strength increases. In this, the D1 is equivalent to D6 because one electron in D1 configuration for the D6, after the half filled, it has one electron. So D1 and D6 are equivalent. Likewise, D4 and D9 are equivalent. In the D4, one electron short. Likewise, D9 also has one electron less than the completely filled shell. Now, the D terms split into EG and T2G in the case of octahedral field. Octahedral field means E is at the top, the T2G is at the bottom. Here, see the D1 and D6 octahedral are D4, D9 tetrahedral on the right side. In the left side, D1, D6 tetrahedral and D4, D9 octahedral correlation diagram is shown. It is coming under one electron, one hole formalization. Now, we will see about the correlation diagram for D1, D4, D6, and D9 configuration. In the Orgel diagram, one electron, one hole formalism is adopted for D1, D4, D6, and D9 configuration. The energy is represented in the vertical dimension and ligand field strength in the horizontal dimension. And the vertical line in the center of the diagram represents the gaseous ion where there is no ligand field strength. The right-hand side of the diagram applies to D1 and D6 ions in octahedral field or D4, D9 ions in tetrahedral field. This situation arises because the ligand field starts splitting and the states are inverted for the two cases. And one electron, one hole formalism also causes the orbitals to be inverted. As a result, the ligand field states are the same for a D1 ion in the octahedral field as they are for the D4 ion in tetrahedral field. The left-hand side of the Orgel diagram applied to D4 and D9 or it is octahedral field or D1, D6 ions in tetrahedral field. The combined D1, D4, D6 and D9 configuration into a single diagram is called Orgel diagram, which describes in a qualitative way the effect of electronic configuration with one electron more than half filled level, one electron less than full shell, and one electron less than the half filled shell. The Orgel diagram for a D1 and D9 ions is inverted by going from an octahedral to tetrahedral field because the Orgel diagram uses a single representation for octahedral and tetrahedral field. In the case of octahedral D1 and D6, the transition takes place from a doublet T2G to doublet EG. For D4, D9 octahedral complex, the transition from doublet EG to doublet T2G. For the tetrahedral, D1 and D6, the transition takes place from doublet E to doublet T2. For D4, D9 tetrahedral, the transition starts from doublet T2 to doublet E. From the Orgel diagram, it is apparent that D1, D4, D6, and D9 ion should give only one absorption bands. Now let us see about correlation diagram for D2, D3, D7, and D8 configuration. The Orgel diagram for D2, D3, D7, and D8 configuration have F spectroscopic ground state. This diagram also includes P state, which has higher energy because in an octahedral ligand fail, that state become a T1G state that has the same multiplicity as that of ground state. So we have to include the P state also for the F spectroscopic term. Therefore, the spectral transition or spin allowed between the ground state and the excited state arising from the P state. Terms or energy states have same symmetry interact so that the energies never cross. Now let us see about the Orgel diagram for D2, D3, D7, and D8 configuration. Here the F is in the ground state, the P is in the excited state. Here also a graph is drawn between energy versus ligand field strength. Here 2 electron, 2 hole formalism is adopted. In this case, the F term is split into A to G, T to G, and T1G. The P term is transformed into T1G for the octahedral complex. Here, see, the center is zero ligand field. The field increases from when we move from 0 to right hand side as well as on the left hand side. On the right hand side, D2, D7 octahedral or D3, D8 tetrahedral is depicted. On the left hand side, D2, D7 tetrahedral and D3, D8 octahedral is shown. In the case of D2, D7 octahedral, there is no similar state. So they cross each other. But in the case of D3, D8 octahedral, there are two terms, that is T1G from F orbital and T1G from P state. So that same state do not cross each other, they move away from each other, they bend away from each other. That is called a non-crossing rule. Here, the states strongly and interact and repel each other. This phenomenon is often referred to as non-crossing rule. The terms or energy state of the same symmetry interacts so that their energy never cross. The terms of same symmetry obey the non-crossing rule, which states that if the increasing ligand field causes two weak field terms of same symmetry to approach, They do not allow to cross, but bend apart from each other. So the diagrams are curved. Yes, see, it is curved. So only we have to tell that the symmetry or same means it obeys the non-crossing rule, which states that the they do not allow to cross, but bend apart from each other. In the case of high spin D3, D8 octahedral and high spin D2, D7 tetrahedral, which is present on the left-hand side, the transition takes place from quadrat A2G to quadrat T2G under the F term, quadrat A2G to quadrat T1G for another F term, quadrat A2G to quadrat T1G for P term. For D2, D8 tetrahedral, D2, D7 octahedral on the right hand side, the transitions are three. That is from quadrat T1G to quadrat T2G F term, quadrat T1G to quadrat T1G P term, quadrat T1G to quadrat A2G coming under F term. Now let us see about MCQs. In Orgel diagrams are applicable only to. Generally, Orgel diagrams are applicable for high spin complexes. That is the answer for the first question. The second one is, which of the following is not shown in an Orgel diagram? Orgel diagram are shown for the allowed transition. Allowed transition means the delta S should be 0. There is no change in spin state. So spin allowed transition only gives Orgel diagram. The spin forbidden transition is not shown by Orgel diagram. It is shown under TS diagram. So the answer is spin forbidden transition. So the Orgel diagrams are qualitative and only valid for high spin complex. The TS diagram gives qualitative and quantitative manner, but Orgel diagrams gives only qualitative and also valid for high spin complexes. The fourth question is, Orgel diagram provides information about energy level diagrams of central metal atom. In Orgel diagrams, the terms are split according to the geometry of the complex. That is, Orgel diagrams in the case of octahedral as well as tetrahedral complex only shows this Orgel diagram. So the geometry of the complex only split in the Orgel diagram. Thank you for watching. Bye-bye.